Okay, so monadic parsing. So consider the following data type. It's a common one that we use when defining recursive data types. It's just a simple data type for encoding arithmetic expressions that are comprised of integers, additions, and multiplications. Now, for today, we're not going to worry about negative numbers. Just to simplify things, let's just imagine that we're writing a parser for positive integers only. So suppose this data type shows to a string, because the way that it's encoded to the computer isn't the same way that we'd want to see it as a human. So suppose we have the following rules that get implemented when we show this data type. So we drop the val decorator. We don't need to see val2. You can just write it as 2. We're going to use infix operators plus and multiplication rather than add and multiply. And we're not going to display unnecessary brackets, noting that both addition and multiplication have higher precedence than addition. So here, the objective really is going to be to take that expression, that string, and parse it into this data structure. Right? So this data structure would show that, and parsing really is the sort of piece of technology required to like reverse this read, right? So this is really today's objective. How can we take something like this and read it as a string and return this? So we've been working with state transformers, and then we've managed to show that these state transformers are monads and functors and applicatives. A parser is effectively a state transformation where the state transformation that we're making is over a string, right? So you're always going to have the part of the string that's been parsed and the remainder of the string that has yet to be parsed. But there's going to be one difference between a parser and a state transformer, and that is that a parser can fail, right? Obviously, not all strings can be represented by this expression data type, right? In particular, the ill-formed ones. So let's just start coding this up. So what I want is a new type for a parser of A. And what I want this to do is take, I have to be careful about this. It takes a string and it's going to return a tuple of A and string, but it's going to be maybe this. And because we're going to want to make this an instance of a functor, yes. Did I? Oh, yes, sorry. I need more drinks of coffee. Yeah, string to maybe tuple. That's better. Now, why is it not colorized? Where's my slides? Give me a second. Yeah, it should be right. Parser of A is a string goes to a maybe string, and then we have to put a sort of decorator over it since it's a new type. Let's just read this in. Perfect. Okay, so everyone understands what a parser is. It's just something which, given a string, returns a maybe tuple, where the second part of that tuple is the string, the remaining piece of the string to be processed. And this is the string that has been processed already, right? So it could be a string, it could be a partial expression. But remember, when I say parser, you just think string to tuple. Okay, because we have this decorator here, it's not a bad idea to come up with a convenience method, which given a parser P, just removes the decorator. Okay, so something like this. P parser. And what you want to do is you just want to parse instead. Do I need to give this a second? Yes, I do. Okay, something like this. And so here's a convenience method, parse. It's going to take a parser over A and a string, and it's going to return a, geez, what is it returning? Should be a maybe tuple. Right. Okay, so we have a type, and now we have a parser, and we can't really do anything with it, but at least you know that everything is typed properly. So now what I want to do is make this parser an instance of a functor, a monad, and an applicative. But you learned in tutorial last week that it doesn't matter how you actually define these, which is pretty neat. And it turns out that if you can actually use the monad instance to define the functor and applicative instance. And if you do that, defining the applicative and functor become quite easy. So let's try to define a monad instance for this parser type that I just made, and then do the applicative and the functor. So let's just remind ourselves what a monad has to be. So a monad is something from this class where we have to minimally define return in this bind operator. So let's just do that. It's instance parser. Is it where? I always forget the syntax for these things. Yeah. Instance monad parser where, and we need two functions here. The first one is return, which given A returns a parser over A. And the other one is the bind, which given a parser over A and a parser, and A to a parser to B gives you a parser to B. Okay, so let's just try and implement these things. What's like the simplest parser that we can write? What do you think we should return in this instance? Yes.
Taking the string and then just return just for whatever the return was and yes, so don't modify the string.
Yeah, so just pass through whatever string that you were given, just pass it through. Okay, so how should this return look? So it needs to be a parser, right? So return has to be something P, and it has to be something that's a function that takes a string to something with A and string. So I think we can, how did I do this? I have to be very careful. How did I? Oh, I'm silly. Yeah, there's an A here. Return A is a parser, which given a string returns A in that string. Yeah, I was discussing with some other students last week. They're saying, well, how do we define these monads and functors and applicatives? And it's like, there's barely, because we're working at such a high level, there aren't many functions actually that you can define that type properly. Remember all the way back at the beginning of the semester, assignment 1, when I said define functions with the following types? There weren't many. In some cases, there were like exactly one actual function. So I don't think there is anything else we could have defined here. Right, I needed to return a parser, which is something that takes a string to a tuple of A and string. Here's the only A we have. We can't do any operations over it because we have no instances, or we don't know if it's part of any class. And it had to be a string function. So here's a string that goes to a tuple, and the first thing had to be A, so we had to put that there. And the second thing had to be a string, and this is the only thing that we have for string. Yes. Oh, yes. Always remind me about this. This is why I hate working with the maybe data type. Okay, so it should, yes. Oh my Lord. Sorry guys, tired today. Okay, there we go. Let's just check. Yes. So maybe I'll just put some brackets around here just in case. Okay, so how can we now define the bind operator? So the bind operator is something that takes a parser over A and a function which takes A and gives you a parser over B. I'll write it like that. What's a function that we can define here? How can we do this? So remember, this has to return a parser, right? And this has to be some type of function which like returns a tuple. Right? So it seems like we're going to want to get the A out of this. And then we're going to want to use the A to get a parser from this. And then we're just going to return it, right? The thing that this function does. So we somehow need to grab that A. How can we grab that A? I don't want to look at my answers. once we get the monad done, everything else falls quite well. Okay, so given a, okay, let me just cheat. Right. Am I losing my mind? Right. Okay, so we take, yeah, it has to be a function which takes C's. And we have to build a function. So I'm just going to use a case statement. So let's take case. Let's put C's through the parser. Do I have to parse it? Yes. So let's parse PA of C's. Where. And then this should give us an A. Oh, I'm losing my mind, guys. All right, that's how, yeah. If this is nothing, right, then we pass through nothing. And if this is, yeah, just A and some new string, then we want to return, let me write this down and then we'll just talk through it. I shouldn't have tried to do it like this. Okay. To bind this parser to this function, we need to return a new parser. So that's why this P is here, where a new parser is a function that takes a string to a maybe tuple, right? So I'm going to send the string through this parser. That's what it does. And if it's nothing, then we just send through nothing, right? The parsing has failed. If this is equal to a just tuple, specifically this just tuple, then we've managed to extract our A. We give that A to F. This becomes a new parser, which we give a string, and then we have to send it through the this parse function just to strip the P. Right. So in fact, this is going to return a parser over B. Any questions? Yeah. Oh, sorry, not F. FAPB. Yeah. A function which given A returns a parser over B. Yeah. Yes. Oh, geez, guys. Didn't get much sleep last night. Sorry. Yeah. Pardon me? There's 2 more errors. Okay, where else am I error? No, this should be like this. Or well, yes, not the, yeah, this shouldn't be here. Yeah, thank you. Thank you. You were right. Yeah. We're going great, guys, right? I'm reminded, just don't forget to fill out a CCAT. That would be great. Please do fill out these CCATs. I didn't let you guys know, but I had my confirmation hearing like 4 weeks ago. You know what that means? They decide whether they keep me or not. And so I had to go like interview for this job again. There were like 10 people sitting around a huge table and I got grilled, but I got it. I kept my job. Thank you. Yeah. Oh, because I would have quit. I would have rage quit this, right? I said, you find someone else to teach COMP3400. Okay. But the point is, I still need to like move up the ladder a bit. I'm a lowly lecturer. I would like to become a senior lecturer. This would put me in a position where I could start affecting change. So if you could write some CCATs for me, that would be great. I'm not even asking you to give me like great CCAT scores, although those 5s go a long way. What I need is for like as many people to fill one out as possible to mitigate against the fact that there will be people who will just take the CCAT and write 0 down every column. Right. So those outliers really hurt if there's like a small population size. So it'd be great if you guys could just like pad out those outliers, right? Because if you think like if 3 people answer and like 2 give me all 5s and 1 gives me 0, that like already makes it so that I have to, if I get anything less than a 4, I get like called in and have to like explain myself. So the uni regards a 4 as like the base of where our teaching should be. So please do fill out a CCAT. I swear this lecture will go better. Okay, so we got the monad. Let's just ensure that there are no errors here. Of course, there are errors. Pardon me? CS dash here?
Yeah.
I don't think so. I think that's fine. Oh yeah. I thought that just was inherited. Okay, so let's do that. Yeah, this is tough because we won't be able to compile until I have everything set up. Okay, so let's do the monad functor now. This should be easier. What's wrong with me today? Yeah, functor for a parser. Okay, so let's just see what the rules are here. Functor. So we need an F map. Shouldn't even have to look that up. Okay, so we need an F map routine. And this F map takes a function that goes from A to B, something that's a parser over A to something that's a parser over B. Okay, so given now that we have the monad, which I expertly and without error implemented on the first try, how can we define this map operation? So just look at the typing information, right? I have fmap. I have a function that goes from A to B and a parser over A. And what I want to do is return a parser over B. So like, let's use our language here, right? Like I want to reach into that parser and grab that A and then put it through F and then wrap it up again. So what does that sound like? Yeah, it sounds like the do, right? So do, so go ahead. Yeah. But don't worry. Okay. So let's pull A out of the parser for A. And then let's just return FAB of A. There's our functor. Yeah. So you can still define it like normally without using the do notation, and it's in the slides. But why not use the monad? It's there, right? Mutual recursion is awesome, I guess. Okay. Instance for a applicative parser where, and let's just look up what we need for to be an applicative. We need a pure function which takes A to a parser of A. And we also need the applicative apply, or I don't even know how to call this, the applicative. So this is a parser which has a function A to B, and then a parser A, and then a parser B. Okay. So this essentially is like the same thing as return, right? Oh, yes, sir.
So how we're looking at like how you can define functor in terms of monad, even though monad requires functor.
Yes.
Would it be a problem if you somehow used like fmap within monad?
No, I think that's okay. That's mutual recursion. That's fine.
But even though it's circular,
That's mutually, yeah, it's mutual recursion. That's fine. Right? It's not circular, it's mutual. It's mutual, mate.
Functor, like if you define a functor in terms of monad and then a monad in terms of a functor.
Wouldn't one just call the other and then the other just call the first? What's wrong with that? What's wrong with F calling G and G calling F? As long as those recursive calls are smaller than the ones before. It's too late in the semester for your mind to be blown. But yeah, this is really, really cool. If you think this is cool, you wait till we do the alternative class and I'll show you a truly amazing piece of mutual recursion. But does that make sense? Like it doesn't matter if you, yeah.
I'm just thinking of the monad as like requiring the functor to be defined, but like
it is defined. It just happens to use it, but be defined using the monad. Yeah. Great. Good lesson. Okay, so this pure is effectively the same thing as return. I'm not sure I'd be able to do this. It would work. I think Haskell would prefer the opposite though. Okay, so I'll do this, but I'm pretty sure this is going to give me a warning. Okay, look here for error first. Otherwise, I'll just dump it. Okay, so what parser can we now define? So I have a parser from A to B. I have to applicatively map this to a parser over A. We're going to use our monad because mutual recursion is awesome. And then, okay, so what do we need to do? So I need that function from inside the parser. Let's get it. So here's F. I'm going to get it out of that parser. I need to then get A out of the next parser. And then I need to be very, is it just F of A? No, it's just F of A. F of A already is a parser. Okay, let's think about it. Okay. Oh no, yeah, F is just, yeah, F. Okay, that's why I should do this. F goes from A to B, right? And this is A. So this is B. So yeah, that's a parser over. Okay. Let's cross our fingers, friends. Oh, by the way, the Maple Leafs lost. No, that's why I've haven't been sleeping for days. Okay, this is exactly what I was saying. It's saying don't do this. Yeah, I think it's so Haskell is going to be removing return, I think, soon. So I think what they would much rather us do is this. Oh. Pure A. Yeah, pure A. Oh, yes. Return equals pure. Good. Okay, no warnings. Because of a weird Haskell prejudice. Yeah. I'm not sure. Oh, okay, fine. Yeah. I think that's another reason like this. Yeah. I don't know. That's why they want to remove it, because it's a little bit confusing that it's still included and exactly identical to something else that has to exist by the time that you write this, but we can still use pure and return. Right. I'm just going to leave it in because it's sort of, I don't know. It doesn't matter. Okay. Return equals. Okay. So we have now a parser type, which is something that takes a string to a tuple where the second part is a string. That parser type is a monad and a functor and applicative. So this means that when we're working with parsers, we can use the do notation, which we have been doing. Okay, what's next? So what I want to do now is take this parser type and build something called derived primitives. This is a word that Hutton uses in his book, but it effectively means in order to parse, we're going to need a handful of basic functions that are going to be the most basic functions for parsing that we can imagine, right? So we had derived primitives for IO, right? Read a character, write a character. Everything else is extra, right? As long as you can read a character and write a character, those are a sufficient amount of derived primitives for doing IO. What do you believe the derived primitives should be for parsing? What are the things bare minimum we're going to have to do for parsing strings? And given string parsing is an IO procedure, it's going to be similar to the derived primitives for IO. You need to read a string in order to convert it into a different data type. Bare minimum, you have to do what? You got to be able to parse a single character before you can parse a string, right? So I'd imagine that having the ability to parse a single character should be one of our defined primitives. Okay. So we're going to write a function called one, and one is going to be a parser over char, right? So it's going to allow you to parse a character. So let's write this. So one, that's a parser over a char, and this is an action. And it seems strange that this is a function that doesn't seem to take anything or return anything, but like IO, parsing is an action, right? It's going to perform a bunch of things in its do block. So how can we get one character out of a parser? Let me think here. So we're given a parser over char, We need to get one character out of that. Oh, right. So at this point, we just have to sort of write it. How do I get a parser over char? No, that's not like that. I need a parser over char here. So this is going to be a parser, which has to take something, which is a function, right? So there has to be some type of parser here, where what should our parser do when given a string like this? Well, it should return just C's. Right, this is a function which takes a string and returns a maybe tuple, where the second part of the tuple is the remainder of the string to be parsed. And the first thing in the tuple is whatever this is. And in this case, we're just saying it's going to be a character that we're pulling out. Otherwise, what do I do? Well, it's just nothing, right? I can't. In every other case, I'm going to be trying to parse out something empty. Okay, so we should be able to already be able to use this. So I can say something like parse 1 out of Drizzy. Should get D. See how that worked? So I got a string back. I got a just tuple back, where the first part of the tuple is the character that's been parsed, and the second part of the tuple is the remaining string to be processed. Yes. No, it will fail. Oh, wait. Well, hold on. Oh, God. Yes. It should be that. Yeah. Parser of anything. Yeah. Okay, that's better. Okay, so now it fails when it's supposed to fail. This should give us, yeah, that. Okay, what's next? One if. I want to parse one character provided it satisfies a condition. So we're going to define something like this. One if, there's my predicate statement, and then there's the parser. Okay, so let's try this. One if I want a predicate that takes a char to a bool, and then I want this to return a parser over char. So how can we do? There's a couple of ways that we can do this. So we got to write another. So this has to be a parser P. So this has to return a parser. You can do this in a couple of ways. This is the dirtier way. So we basically do something like this. I have to do a. Here's a predicate P. Now I'm tempted to utilize the fact that this is a monad, but let's not. Well, we can. Okay, you want me to write this like from scratch like this, or use the monad? From scratch. Okay, so I need to do something like P is a parser, and that takes a string C's to. This may be harder to do from scratch, because now I need a case statement. Well, it's something like what happens if it's empty? Okay, let's see. Okay, so I need a parser C over C's. Then I need a case statement PC. Is it of or where? Of. And if this is false, then I want to return nothing. No, I can't. It's too. I'm going to use the do. We had all this problem setting up the monad. We may as well use it. So I want to grab one character out of the parser. And then if it is true, then I want to do something. Else, I want to do something else. So what should these two branches be? So I need to return a parser over char. So what should I be returning here? Is it just X or return X? Okay. What about here? here I have like return a parser, right? That's what we're obligated to return, but what parser do we return? This is the failure case, right? This is a little bit tricky. It's a parser that always returns nothing. It's the empty parser. So this should be a parser that always returns nothing. So this should be something like return C's goes to nothing. The empty parser. Yeah. Oh, yeah. Should have P. Yeah, that decorator. Yeah. So let's just type this. Oops. Oh, yes. Jeez. Okay, so now we can do something like, okay, let's just define a method here for is lower. So given a character, I'm going to give a bool back. So how can I ask if a character is a lower character or not? So on your exam, you don't have access to the internet. Quick and dirty, how could I check for lowercase characters? Yeah. No imports. Yeah. Quick and dirty. That gets you lower elements. You don't need fancy imports. You just use these strides. Okay, so I should be able to do something like, whoops, parse one if is lower from Drizzy. I have a is lower. Yeah, okay, there we go. I didn't save. How do you know that I didn't save? Is there like an indicator here? Oh, is that what that circle means? Oh, you guys, the students have become the teacher. Okay. Okay, so there's me parsing one if lower, but if I were to capitalize Drizzy, then you get like nothing back. Cool. So I'm going to keep building more primitives. Parse one digit. Okay. So I want something like digit, and this parses, let's say integer? Oh, char. So I guess it parses a character digit. It doesn't convert it into anything. So how can I get a digit out of here? What parser do I write? Yeah. Exactly. Huh? One if, oh yes, you're right. Lambda. No, I don't need lambda, do I? That's just a, shouldn't, not, maybe I do. Okay. Oh my God. Teaching two languages in the same day is really hard. Okay, so let's see if I should be able to parse a digit from here. Cool. And I shouldn't be able to parse a digit from here. Great. What next? So we're going to introduce another type class, which I haven't done for a while, I guess. So some of the type classes we've been working with, right? Like numbers, ordered, equal, functor, applicative, monad. The final type class we're going to be introducing is this thing called the alternative type class. And how the alternative type class works is that if you have a type where there's like obvious degenerate outcomes, like the empty string or empty list or nothing or left, this applicative, this class is going to allow you to designate alternatives to those failure cases. So here's how it looks like. I don't think it's not, you actually have to like put this into your text file. This is not part of the prelude, this applicative or this alternative, but anything that's an applicative can also be an alternative. provided that you define these two functions. The first one is basically tell me what the degenerate case is in this type. That's what empty means. And then this is the alternative infix operator, right? So given A and A, give me back A. Here's how we can use it for maybe. So I just have the alternative class here. I'm going to copy it in. Let's copy it in to here. Okay, so here are the rules for being an instance of a alternative. And here's how we define the alternative for maybe, right? The degenerate case is nothing. And how do I choose, right? I'm saying, well, if nothing, alternatively, maybe Y is maybe Y. Maybe X, which at this point cannot be nothing because that would have triggered the previous pattern. Alternative anything is just maybe X. So let's just load this in. So now I can say something like nothing, alternatively, just one. Right? Or I can say just one, alternative to just two. Right? Or I didn't define one for either, but it works similarly. So now what we want to do is define an instance for alternative for parsing. So let's give that a try. And what this is going to allow us to do is provide alternatives for when a parser fails. And parsers are going to fail a lot, right? Because the way that we sort of write parsers is at every step, we're going to try every available parser. Right? And one of them is going to succeed and we'll move forward like that. Okay, so alternative for a parser where what is our empty in this case? What does an empty parser look like? We've already used it. We used it up here. That's the empty parser. So actually, we could just write empty here once we're finished writing this alternative. Okay, so here's our alternative. So empty is this. What about the choosing between two parsers? So this is something like, here's a parser of A. Here's one parser. Here's another parser. So parser 1, parser 2. So how do I select between two of them? Yeah.
And then you try and pass that through both passes and you use the maybe version.
Maybe that would work. Yeah, I want to use the monad since we have the monad. Like, I'm not saying what you said won't work, but we're going to end up having to thread all of the nothings through, which is like kind of why we introduced state transformations. So again, I'm not saying what you're recommending is wrong. I just think that utilizing the monad will make it a little bit more clear. So how can we use the monad in this case? Well, there's no function. It's just they're holding A. So it's something like I want to pull A out of the first parser, and if like that doesn't work, I want to do something else. Any more ideas? Yeah, I'm just going to pull it out here. Where did I write it? Oh, that's not right. It's here. I closed that. God damn, I hate that panel. Where's my alternative? Let me make sure to do it right here. And maybe calling that B wasn't the greatest idea. Okay. parser of A naught, parser of A1. This is parser of A1, parser of A naught. Okay, so I have two parsers here. So I didn't use the do. Okay, so apologies double time. I guess I need more coffee today. But what happens here is that this needs to select between two parsers. So the answer has to be a parser. So that's why that P is there. And what's a parser? Well, it's something that takes a tuple to a maybe. It's something that takes a string to a maybe tuple. Right? So I'm going to try to parse C's. This is exactly what you said, right? I'm going to try to parse C's through the first parser. And if it doesn't work, I'm going to try to parse it through the second parser. And if it does work, I'm just going to pass it through. Does that make sense? If it doesn't make sense, let me know. Right, but if effectively, it's just saying, try the first one. And if it works, send her through. And if it doesn't work, try the other one. Okay. Let us parse all consecutive digits. That is, while is digit is true, let's parse something. So let's introduce a while. So how can I sum. I want to define a function sum, okay, which takes a parser over A and returns a parser over A, while is digit is true, right? So sum is going to parse all consecutive digits. How can we do that? And we've given some parser of A, and given that we have a monad. Well, can I reach into the first parser and grab an A? What do I need now? I guess this has to be parsing numbers. Yes, sir.
Would you do something like is where you could do like a case of the one where you pass the digit, and if you get nothing, then you stop. Otherwise, if you recursively call the parser.
Yes, right. So this is going to be a parser that we're going to want to keep calling. So it's actually more generic than just testing is digits. This is going to work over any parser, right? So we have to imagine that this sort of is digit, but given this parser, I want to pull one thing out of it. Then I want to pull many things out of sum of PA. Is it PA? Yeah. And then I want to return the list. All right. But here's a problem. What happens if this fails? Then the whole thing returns nothing. But if this succeeded, then that would have been wrong, right? You want to return one thing, not nothing. So how can I fix this? What should our parsers do in this case if they fail? Yeah, return, not just empty, pure empty, right? Or return empty. Yeah, put it back into a parser. So I'm saying, give me a parser, take one thing out of it. Now try to take the rest out of sum. And if that fails, just imagine that you get alternatively, you're just choosing empty list rather than nothing. And if it works, great, then you have a string, and it's going to return their concatenation. Okay, so let's take a look about how this could work. Okay, so I want to parse some digit from here. All right, if I put this here, it wouldn't work. All right, I could also say parse some is lower. Oh, is lower isn't a parser. Yeah, I'd have to do one if. Yes. It can't return it, like you mean a parser over an empty list?
In the case where nothing is satisfied. Nothing. So basically, instead of nothing there.
Mhm.
have it return just empty ACS.
It's like parsing the empty string, I guess, which has no meaning. Like you could just do it. Like I want this to fail by our design, because like basically I'm going to say, here's an expression. Try to parse all of its digits. And it's like, well, this doesn't have digits. And you're like, oh, that failed then. So try now parsing a plus. So this actually is like what we want this to fail, right? For our parser. And when I say try to parse this out of here, and it can't, I want that to be nothing rather than like the sort of empty list, which is just like a different designation for that degenerate case anyways. Like how different is it really over nothing, except that nothing sort of has this automated behavior of being passed through our monads. Okay. Yeah, it's tough. It's because sometimes when we define things, it's defined the way that we've defined it because we need it to be defined that way. Maybe it'll become more clear once we implement the parser. Yes, sir. Yeah, you'll get an empty string in there's nothing left to parse. Cool. But that's in the second position. That's different. The second position is holding the text, which we are currently parsing. And it's in particular, it's holding the bit of text that is yet to be parsed, right? The first position is going to be parsed stuff, whatever that means in our context. Okay. Many. We also want to define the convenience method for parsing 0 or more digits. In this case, parsing a string that starts with a non-digit will return a parser encapsulating the empty string instead of failing. So this is what you wanted to do for many. So how can we write this? Right? We want a many, which does this, which rather than returning nothing is going to return, as our colleague over there said, a empty in its first position. How can I do that? Well, many is pretty close to some, right? It differs in one condition. Where does many and some differ? So some is we parse 0 or more things, and many with some we parse 1 or more things, and with many we parse 0 or more things. Yeah, yes, literally, yeah, that's what I just said. This is exactly what you wanted to do. So would you be able to implement this many? Right, so it's obviously I want to do some, but what happens exactly? I think it's pure, right? I'm just giving an alternative to like this single case where some fails. I'm like, okay, if it fails, just return like the empty string. Or yeah, I guess it could be an empty string or an empty list. Yeah. If it failed. So some digit 1, 2, 3 ABC should work. Whoops. I have to parse that. I have to use appropriate bracketing. Okay. But it won't work if there's an A here. It failed. It failed to parse 1 or more characters. Whereas if I do many, this is not going to fail. It's just going to say, but like I just wasn't able to pull out any digits. And so there's like a slight nuance here between what they both do. Okay, my dual recursion friend up there, or mutual recursion. There are higher order patterns for some and many that work over the entire alternative class, believe it or not. And those are them. We could have used these one-line functions for some and many. Is that incredible that like even that has a higher order pattern associated with it? So this would have worked instead of anything that we wrote. We wrote some and many for like presuming we're working with a parser, but actually that pattern will generalize to anything that has like alternatives, right? Because some is like, okay, like keep giving it to me while we're not failing. And many is like, well, keep giving it to me while we're not failing. And if you can't do that once, then I'll just give you back. Like this is what we wrote for many, actually. Right, so we had half of it. So this was really astounding to me that even that pattern could be generalized. Okay, parse a digit and return it as an int. This is a little bit different than what we had written before, which was called digit. So how can we parse a text digit but return an integer instead? So it's going to be something like a parser that gives you back an integer. Okay, so what do we do in order to like read some text read a text that's going to definitely be a number and then convert it and then put it in the parser? Okay, one step. Oh, yes. Yeah, draw A from digit. Digit's a parser, remember? So I'm saying, okay, grab me, is it not digit? Many digits. Or I guess some digits. Oh, geez, we have to be careful here. I think it's some digits, right? Because I want to parse an integer. So if I can't, it should return nothing. So I'm saying, okay, here's the string, parse a digit out of it. Right, and it's A. A is now a string and it's a digit. And then I should be able to just return read A. It's going to know that this read A should be an integer because of the inference, type inference. Did I do that right? Oh yeah, some digit. Okay, let's try. I wonder if it's going to be able to show this. Okay, so let's parse a natural number out of this. Aha, quotes are gone now. So what happens if we try to parse a number out of here? Nothing, can't. Cool, all right. Parse one character. Well, that should be easy. Character, parser of a character. So I want to do, didn't we do this already? Oh, we want to parse a particular character, right? So I want to do one if equal to C. So that's something like parse maybe character, and just to give you an idea why we define this, like maybe plus from out of here. Okay, so it allows us to parse one character. If this was a multiplication, then we would have got nothing. So we can parse natural numbers and we can parse single characters. Let's parse a string. So that's the same thing here. So this is a string. Given a string, I want to return a parser over, is it string? Yes. How can we do this? So here's a string. And I want to basically do what char does, but like many times. Want to use the do? So it's something like parse the character C, and then then do this. And then I guess return it. So this is going to be strange. I don't need to do that actually. So that will just parse it. That will just parse it. That should work. Okay. So I can say parse the string ABC from ABC123. What? Did I make a mistake somewhere? Am I in the wrong monad? Oh, hold on. Yeah, I have to be in a different monad. This one's tricky. Line 2. No, I think. Yeah, I have to be. Yeah, it's getting yeah. So okay, X has to come out of this. That gives you a single character. Then X comes out of this. This gives you a string, and that's what I want to return. Come on. Oh, base cases. Lord. So what should the base case be? So it would just be empty. Yeah. Yeah. What did I write here? Okay, maybe you're right. Return empty. Let's try doing this. Come on. Okay, it worked. Now we can pull out strings. We can pull out strings. We can pull out characters. We can pull out numbers. We can pull out symbols. We've done that. Parse and throw away space because we don't care about spaces. So we don't want to actually grab them. We just sort of want to like throw them away. So that's why this is going to be a parser over the null, like the empty tuple, because this is an action. Remember IO of empty tuple? There was an IO action that like didn't encapsulate anything because the only thing we wanted to perform were actions. So this is sort of the same thing. I don't actually want to return anything. I just want to skip a bunch of spaces. So let's try to write space. And this is going to be parser over nothing. So how can I read a space, like arbitrary amounts of space? Or is it arbitrary or one? Okay, all of them. I want to throw away all the characters. Yeah, I think it's sum in this case. So sum, if I want to parse some characters that are space. And then I want to return, I think, empty. Yeah. Oh, many. Okay. So let's try to parse some space from here. Cool. So it's like I've thrown away the space. How come some wouldn't have worked? Or would they have both worked? Let's see. Just curious. I think that's the. Yeah, okay. That's the difference. When parsing, ignore surrounding space. Okay, so I want to be able to say something like, go grab plus, but I don't care if plus has like space in front of it or space after it. So go grab space, then plus, then space. So that's what this tokenizing is going to do. Whoops. So I almost put my hand over my screen to cover the answer from you guys. That's the state of my mental energy right now. So I basically want to be able to say like parse a digit from this, but tokenize it, right? So I can grab that and it's going to just return, oh, well, that I have to tokenize many digits, I suppose. But again, I want to get rid of all the space in front and behind something. So that's a token. It's going to be a parser over, yeah. You give me a parser and I'm going to give you a new parser that like automates the removal of the spacing. So it's something like, okay, so do space, and then grab this out of the parser, and then do space, and then return it. Yeah, does that make sense? Because in a do block, it's just sort of actions that we're like performing. So I should be able to do something like parse token char plus, and then blah, 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 spaces. Ah. See, grab plus, who cares about space? And there's like the remaining thing to parse. Okay. So now what we want to do is put this into practice. And we want to use our parser to like implement a grammar. So we're going to do that now. So we have all of the derived primitives, right? So let's just take stock of what new tools we have. I can, given a string, I can read stuff from that string. I can read specific characters. I can read specific strings. I can read numbers. I can convert those numbers into integers. And I can also ignore white space while doing all of these things. So that should be enough derived primitives to accomplish the next. Well, remember the original task was given an expression like 2 + 3 × 5, convert that into the original data type. Okay, so that's what we're going to do next. Grammars. So this is why this is like, I really like parsing in Haskell. Parsing in Haskell is like one of its main uses. This is why Pandox is written in Haskell. Like parsing just works out really elegantly. The problem is we've done most of the legwork already. Like we've written all the parsing tools. The only thing left to do now is write a grammar and then implement that grammar using the derived primitives. I guess what I'm trying to say is like, once you are given the grammar, implementing it is trivial. It's like almost like one-to-one from grammar to Haskell. So and this can't be a class where I expect people to write grammars, because there's like a whole other course where like the whole course, that's like the point, is to learn how to write a grammar. So I don't know if you have any ideas about like how I could give homework that's not like totally trivial. I'm all ears, but that's why this became sort of like an advanced topic, right? So what I'm going to show you now is just like the basics of grammars. I'm going to show you the grammar for that arithmetic expression that we were working with. And then I'm just going to show you how like trivial it is to implement it, like once we have all of these tools. And you should think, oh, it's not just expressions that I can parse here. It's software itself. Like we could parse Python or C in like the same way. I guess I can say things like grab while, then grab like the predicate statement, then evaluate it, right? This is sort of the beginning of like writing compilers if you want. And so it's just really neat. Okay. So everyone's still with us. Let's check on chat. You still with us? Let's see. I like seeing if chat's alive or if they just log in and then like go play Fortnite or something. Yeah, okay. It took a little bit of a long time to type. Okay, recall that showing is to convert some data type into a human readable output, right? So in order to read, like this is reversing, right? So to show something was easy, but to reverse that show is hard, right? Because we require a parser, we require our one of this. So let's consider an even more basic data type than the one we were using. It's just expressions that are adding positive integers together. We'll add multiplication on at the end. By default, this is what is shown, right? If we were just derive show for that expression. And this is like the best encoding for like a computer. You can imagine like building a machine that could understand add and understand val and know what to do in those situations. Secondarily, there's no ambiguity possible in statements like this, right? The top level structure is telling you the order of evaluation. It knows that this add happens first because it's lower. But we don't write that. Like imagine if we had to write expressions recursively when like doing math, that would be a disaster, right? So although this is a machine optimal way of encoding the expression, this is a human optimal way of encoding the expression, right? It eliminates redundant brackets. It's easier to write down and easier to consume. So I can write a parse tree, which is sort of like a human readable version of the machine readable thing. And it looks like this, right? So the expression was, well, there's really two ways that I can write this, right? The first way is that it's a sum, or it's the addition of the addition of the value 1 and the value 2 with value 3. And that's 1 plus 2 plus 3. Because addition is an associative operator, that is to say, it doesn't matter how we bracket it. We don't write brackets. It would be pointless to write this. It's needlessly polluting the expression, and it's adding it doesn't do anything, right? The brackets aren't doing anything because this is associative. You can just forget about all of them. The problem is, this means if I can add redundant brackets to expressions, there are many expressions that will parse to the exact same. There are many expressions that will show the same string, right? This is 9 plus 2 plus 3 plus 5 plus 7. And there are an infinite number of ways of putting redundant brackets over that expression, but they're all equivalent to that. So to show this goes to here, and to show this goes to here. Well, this is the problem. Why is this the problem? Recall, the objective is for us to try to reverse the show as a read, right? Read is inverse show. But I've now given you two expressions that are different, that show to the same expression. Why is this a problem for the inverse? Okay, so we have a function that's 1 to many. What would its inverse be? Many to 1. Can functions be many to 1? No. So we can't invert this show right out of the gate. It's like mathematically not possible. So we're going to have to figure out how to disambiguate these two, like this and this creates a problem. So show is many to 1, and therefore the inverse of show, read, cannot be a function because functions cannot be 1 to many. That is to say, read is ambiguous because an unbracketed expression could correctly correspond to many elements of expression. To disambiguate this, we just presume that addition is like right associated. We just have to give a rule that says, in the absence of brackets, these are the ones we're going to presume are present, right? And that's enough to disambiguate this. So ABC will parse to this expression with the brackets on the right because of the right associativity, and not with the brackets on the left. Although if we still want brackets on the left, we can still have it. It's just now we put brackets there, and those brackets now are meaningful. They're not, right, because we're saying it's right associative and not like arbitrarily associative. That still has meaning, right? So this will eliminate the fact that we can't reverse the show. Okay, so loosely speaking, a grammar is a set of rules expressing how to generate legal statements in whatever language that you're working in. So the language that we're working in is like all expressions that are adding positive integers together. Our symbols are plus and numbers. Okay, so how can we write a grammar for this? Our grammar must be able to distinguish legal expressions, like 1 plus bracket, 3 plus 4 bracket, from illegal ones, like this one, where it has like an open bracket, but not a closed bracket. Here's how we can write the grammar for string representations corresponding to valid expressions. So what I'm saying is that any valid expression has to be able to, is generated from this list of recursive rules. So I'm saying any valid expression is expression plus expression, or it's an expression with brackets around it, or it's a value. And a value, this is kind of being cheeky, but I'm saying a value is any number, 0, 1, up until the end. Okay, so that is to say an expression is either two expressions separated by an and, single expression surrounded by brackets, or a natural number. We can draw it like this, right? So here's the parse tree showing how 1 plus 2 plus 3 is interpreted by our grammar. So our grammar is going to look at this and it's going to say, oh, this is an expression. And it's an expression that's this, which is an expression separated by a plus and another expression. Okay, so let's look at this one. So what expression is this? Well, it's not a expression. It's not the sum of two expressions. It's not a expression in brackets. It's a value, and that its value is 1. Okay, this second expression is the sum of two expressions, where the first expression is neither the sum of expressions or bracketed expressions, so it becomes a value in 2, and the same thing for the right branch. Make sense? Okay. This different parse tree also can interpret 1 plus 2, right? So we haven't written a grammar which has unique constructability. There are like various different ways of like constructing the same, of parsing this expression, which we're going to fix. So the one we did on the slide before basically did 1 plus 2 plus 3. This one is going to be 1 plus 2 plus 3, and it corresponds to this grammar. Yeah. So it's not about like reading left to right necessarily.
Seems to be like, okay, awesome. Go basically to have seen 1 plus 2.
So, okay, we're going to do it like this by introducing like another type of expression called factor, and factor is going to have a higher order of evaluation. Right, so this is how we're going to make it left right associative, essentially, by adding another rule like this. And like, I would have never expected you to be able to produce a grammar, right? There's a whole course in writing grammars. I'm going to show you once we write down the grammar how easy it is to just encode it into Haskell. But if I add one more rule to our grammar for factors, then I can show you how we disambiguate. So I'm saying an expression is no longer the sum of two expressions. An expression is a factor plus an expression, where a factor can be an expression in brackets or a natural. Oh, why did I put that? That should be val, not nat. Okay, so I'll show you how adding this factor now like will disambiguate things. So here's the expression 1 plus 2 plus 3. So the parser is going to look at this. It's going to say this is an expression. And it is an expression which is a factor plus an expression. That factor is a value which is 1. And the expression on the right is a factor plus an expression. Okay, so 1 plus 2 plus 3 gets this parse tree and it's unique, right? Because we added that factor in. If I wanted to put the brackets over here, or sorry, if I wanted to, this is assuming the brackets are over here. If I wanted to put the brackets on the left, right, which is violating our presumption that it's right associative, you do properly get a different parse tree, right? Because now this is an expression, which is the sum of a factor and expression, but that factor is a bracketed expression. And that expression is the sum of a factor and an expression, where the first factor is a value, which is 1. And the second expression is a factor, which is a value, which is 2. Okay, so all you need to understand is that this is a grammar for reading numbers and the plus symbol in such a way that we're doing it where we're getting unique parsing, right? Because we're presuming right associativity. Grammar to parser. It is a straightforward, exceedingly straightforward exercise now to define a parser in Haskell that implements this expression. So you want to give it a try? It will be cool. Okay, so do I want to do it in, okay, I'll just continue doing it in Sandbox. I just need to grab, well, we need to define some data. Okay, so we have some data, and that's for an expression. Did I say expression over A, or is it just expression? I forget. Yeah, it was just expression. Okay. So I have a value which is an int, or I have the sum of two expressions. Okay, so there's my data. So what I want to do now is like build a parser for expression. There's just one more thing I want to grab. This thing up here. Oh, no, nope, here. This. I just want to grab this. We'll forget about turn. Okay, so we have this. Okay, so here's our grammar. Right, an expression is either a factor or an expression. Expression is a factor plus an expression or a factor. A factor is a bracketed expression or a value, and a value is just like all of the numbers. Okay, so let's try building this. Okay, let's do value first. How can I build a parser for value? So we're going to have val, and it's going to be a parser into integer, I believe. How can we do that? I know. So what do I say? I think it was called nat. Yeah. So do, I want to get a natural number out of nat, like I want to pull that out using the parser. Now I'm holding a number n, and now I just have to sort of return it. But I'm not returning, no, I'm being dumb. I want to write a parser for expressions, not a parser for natural numbers, right? So I grab a natural number from the string, if possible. Otherwise, it will fail, but who cares, right? So I take a natural number out of the parser. It's really an integer. So I want to produce an expression. So what am I returning here? Yeah, val n. And now you see how text is being translated into the data type, right? Because I'm going to pull out something like 1, 2, 3, and I'm saying, oh, you're val 1, 2, 3. This is how you got shown, like things from val 1, 2, 3 goes to 1, 2, 3, and this is how we reverse it. Okay, let's now do factor. Factor is a parser for expression. So we need to do two things. Okay, so we have to be careful here because the do's sometimes get messed up. Okay, so like I want to try and read bracket expression bracket. So how can I do that? How can I try and read a left bracket? Well, what parser do we have that we can read single characters? Yes, car left bracket. Is that what you said? Okay. And then, of course, eventually char right bracket. And then what do we read in the middle? Yeah, which we haven't written yet, right? So from E, I need to get an expression. That will come next because it's mutually recursive. And then what I want to do, return the expression, right? But that can fail. So what should I do if it if it fails to do this, what's the only other option? Val. Okay, so then it's like, oh, or it's a val. It'll work because it's a parser of expression, right? Huh? What should be capitalized? This V? No, it's this, the parser. Yeah. No, that will work. That was why I have my answer here, except I think I tokenized the yeah, I put tokens here just to ignore white space. It's typed properly. That should give us a lot of confidence. Okay, so now what do we need is expression. So let's write one for expression. So expression is a parser over expression. And okay, so we need to do this. So do, I need to grab f, which is a factor. And then what I want to do, then I want to do token char plus. I try to read a plus and then try to read an expression and then return add FE. Right? Add the factor to the expression because the thing I parsed out was the plus. Okay, but if that fails, then I just want to return the factor. But I think that has to be returned because it has to be a parser over factor. Yes. No, because this, why do I need nested do's? Yeah, well, let me run this first, and then we can try to break it. Okay, so it's working in that it's compiling. Let me just try to read an expression. Oh, oops. Perfect. Let's try something. Huh? That worked. It didn't work. There's some, be really careful with the what's the value? Yeah, let me take these tokens out for a second. Let me just look at my answer here because it worked. Okay, this is what I have for my solution. I can't see anything. Okay. How did that and that differ? Oh, it's, yeah, it has really bizarre. If this works, yeah, I don't know why. Yeah. So like this whole thing can be a fit. So like this is like an alternative to the do, I guess. Right. So anyways, you got to be kind of careful with your spacing here as I just, okay, so let's see. I'll go back to here. Aha. See? Here's the expression. Let's try it with some brackets. It still works. I can put +3, right? And it's pulling it out. Okay, so what was the way that you wanted to break this? Well, what is the way that you wanted to amend this? Right? Okay, we got to be careful. Okay, so what this is a parser expression. Well, it's because I want to use the F. Right? If I take out this do, if there's any failure within that do block, the whole thing will fail. So maybe I could do something like this, where I do that, and in the end, I just return factor. Okay, but now I have to parse that factor twice. But either would work. Does everyone understand? Like this works, right? I'm saying, okay, try to read a factor, then plus, then an expression. And if that fails, then return a factor. Whereas in like the first part, I said, read a factor and like save that for me. Then try to read a plus and an expression. And if that fails, just return the factor F. All right, so, but either will work. Maybe I'll leave it as the simplified one, I guess, because who cares about efficiency really? I guess some people do. Okay, so this could be done like that if you want. Maybe that's better. Yeah, maybe I like that better. I'm gonna change my slides because it's more clear, even though it's a little bit less efficient. Yeah. You want me to indent this an extra time? This one?
Yeah.
Oh, when I did that? this here. Will that work? No. Yeah, I just do this. I just do one tab out. I think this is technically what the Haskell style guide says for do's. It doesn't matter. Like, yeah, yes, sir.
It's like little, it's just a silly question, but like, I'm just struggling to understand how we're not, because we're like passing factors in that expression.
Mhm,
we're
this one.
saying F is factor.
Yep.
And factor would be like consuming from the unpassed text in the parser.
Yeah.
But then later on, we were able to do, you changed it just before to return factor, or to just not, instead of return F, you just wrote factor. But how is it accessing the text after it's already been consumed?
Because it's like branching, right? Like I'm spinning up, because it's the way that the state is threading itself, right? The state's not always moving. It only moves when I pass it down, right? So it's like if you have a failure branch, it says, okay, forget everything that returned nothing and restart here. And like this hasn't progressed its state yet. It's hard to explain.
Yeah.
But it's working, right? So if you just go through and try to understand like the derived primitives are working, yeah, it's just the way that these alternatives are being handled. It's like delayed computation, right? So it's like, okay, I'm saying you're here and you have an opportunity to move left with the current state of the parser or right with the current state of the parser. So it tries to go right, and if it fails, that signal is sent back up to here, and it says, oh, I failed on my right branch. Okay, try left branch. But it still has its current state, right? The state only changes as you like make a recursive call, like down, right?
Sure.
Right? So there's still like the original state is still at the top here. Like the first parser we called with everything will always have the full thing there. Right? And if you succeed in one of your branches, then the whole thing is done. Like we don't have to go back up. But it's kind of like make a recursive call that can fail, and I'll just sort of wait here. And if there's a failure condition, then I'll try the next thing. But it's sort of, does that make any sense? It's like you have a tree, and like the node like always has its current state. And then that node can spin up a new node with a new state, but like the original one doesn't change. Right? We don't really have globals, right? Every function is getting passed in the current state of the globals essentially, which means the function that invoked that function has its own state, right? So it remembers the previous values of all the global variables, right? That was sort of the purpose of these state transformations. Okay, so let's just put some extra stuff in here because I just want to be able to tokenize around brackets. So I should be able to do something like this now, hopefully. Okay, so what I want to do as the final thing today is add multiplication now. Right, so there's all the examples here. Oh, we need to do a negative example. What happens if I try to parse this? That shouldn't have worked. Oh, no, it didn't work, right? Because there's what it could parse. And then this is the beginning of the string, which is unparsable. So this is a failure, but with a partial success, right? Whereas if I were to do something like this, like that's just total. I wasn't even able to parse anything. There is no partial success in the parser. Okay, this would be super difficult to do with like an imperative languages for exactly the reason my colleague up there says. Like, how do you maintain the proper state when like failing on one of your branches? That's always going to be a trouble when your parser fails. You have to send a signal back up to be like, hey, revert back to the state that you were in before I failed this. But in our case, the recursion is handling it. Okay, so what I want to do now is add multiplication. And then on your tutorial this week, you're also going to add exponentiation. It wouldn't be a bad idea to try to add negations. Where's my data type? Here. Okay, so now I also want to add the multiplication of two expressions. So this means we're going to have to amend our grammar. Okay, so let's amend our data type to include multiplication. Multiplication has higher precedence than addition, right? So if you see an expression like 1 + 2 × 3, which is fine, we would write this in math. The computer has to understand this is 1 + bracket 2 × 3, and not this way. And we're also going to assume that multiplication is right associative, just to disambiguate things for, in the same way that we discussed how we disambiguated it for the sum. Okay, so how can we amend our grammar to accommodate multiplication? Well, I'm going to add another type of, they're called terms, which is unfortunate because I'm adding a term called a term. But here I'm saying, I'm just adding another level of priority. I'm saying an expression. So we define another rule to place multiplication higher than addition, but lower than bracketing. Because I'm saying, like, if you see an add, that add is going to be the sum of a term and an expression. And what can terms be? Well, terms can be two terms that multiply together, or a factor, which is a bracketed expression, or a value, This still isn't quite enough, because this is not accounting for the fact that we want multiplication to be right associative. So to fix it, we just say in term that a term isn't the product of two terms, but the product of a factor and a term, right? So the grammar just will always move down one, at least in its at the first thing it's looking at. Okay, so we have an expression which can be a term plus an expression, or a term which can be the product of a factor and a term, or a factor, a bracketed expression, or a value, or all the values. So let's just look at this parse tree. So it's 2 × 3 + 5. So this is an expression which is going to be the sum of a term and an expression. This term is a factor multiplied by a term. That factor is a value, which is 2. This term is a factor, which is a value, which is 3. This expression is a term, which is a factor, which is a value, which is 4. Right, so that's how you'd write the parse tree for this expression. And now we just want to go ahead and extend our parser to accommodate that. So here I just have to have something that's a term. And this is going to be a factor times a term, or a what? I said term? Factor. And the first thing should be a term. Okay, so how can we now fix this? So clearly we need something called term. So here's term. I want to parse an expression. And it's going to be effectively the same thing as plus, right? It's this. But instead of a plus, I want that to be a multiplication. And it should be a factor times a term. So here's my factor. Then I need to get a term. And if that fails, it's a value. Okay, it's a value. So that does term. So now for expression needs to seek out a term first, which is t, then a plus, then an expression, and then I want to add that term to the expression, or I want to return a factor. Actually, the new simplification, it's better this way. Because now I need to return it needs to be or alternative factor, not alternative. And anyways, your suggestion is good. Yes. Where? This factor should be a term? Oh, yes. Okay, well, there we go. So let's see. Oh, I think yeah, val. Okay. So let's see, as my final thing for today, can we parse the expression for, what was my example? It was like 3 plus 4 times 5. Oops. So 3 plus 4 times 5 is the addition of the value of 3. Oh, I have to put them all here. Okay. So this is we've parsed this to the addition of the value of 3 to the multiplication of the value of 4 to the value of 5. And like, look, it wasn't that bad. It's like 5, like, do you see my point? Like, if I give you this, it's trivial to write the parser that is equivalent to that grammar, right? Because I'm just putting like this. So let's look at expression. It's a term, then an add, then an expression, and then return this, or it's a term. So my problem is it's unreasonable for me in this class to expect you students to be able to produce a grammar. That's like well outside the scope of this course. But if I give you the grammar and then ask you to implement the parser, then there's like nothing to do. So last year I gave them a grammar with like some blanks in it. I just had them like fill in 2 spaces, but still. A fun example. So one of the exercises practical problems was reading expression with balanced brackets. You could solve that one using a parser, and you should try, right? But the only simpler parser than the one I built for expressions would be one that is just checking if an expression has balanced brackets. So think about how you could write a grammar for that and implement it. Or another thing you can try doing is like adding negation into this. It's you have to be a little bit careful because negations are always weird. Are there any questions regarding this? So this is pretty cool. I don't want to give you the impression that it's only useful for like reading expressions, right? The expression itself can be a computer program, right? Where you could read a while loop and like write out the machine code, right? Your data could be like machine instructions. Your string could be Python code, and your output could be like a list of machine instructions, right? So compilers, talk a lot about what we talked about today, but the parsing in Haskell is really elegant, which is why I really wanted to show it to you. Okay, so this is not going to be on your exam. It was just for fun. That being said, thank you for showing up for an optional lecture. And CCATs, 5-star me in the iTunes store. That would be great. And then next week, I'm going to be giving a review of everything. And then we're going to port all of it, as much as we can from what we learned in this course to Python. I'm going to teach you some practical Python functional programming. See you guys later. Enjoy the rainy day. Okay, bye, chat. Thanks, guys. You too, fill out CCATs for me. I'll send out a reminder. Yeah, parsers, I think this is one of my favorite lectures. Yeah. Okay, bye, everyone. Hi, gentlemen.